Hello everyone and welcome back to the channel. Today we are doing another video in our C and C++ eventually series. Today we're actually introducing a very important topic. Today we're talking about pointers. Now, in one of the previous videos we talked briefly about memory and addresses. And we talked about this idea of passing addresses instead of actual variables because it's more efficient. And we'll we'll talk about um I'll go over the same analogy that I showed you, and we will just point out what pointers are in this analogy. Remember, we said that data is just, we can see it as one long array of just memory. Every single slot is, well, it's a group of bytes. In most systems it's either 4 or 8 bytes. We can assume it's 4 for us. But anyways, so this like long list of array, we can just think of as one street with multiple houses in it. Okay, not too bad, right? Now I want you to imagine this, right? Let's say you are throwing your birthday party at house number, well, 0, 1, 2, 3, 4. Let's say you own house number 3. This is your house right here. This is you right here. And this is your birthday party. Now, you want to go out and you want to invite all your friends, right? So you go to this friend right here and you want him to come to your house. Now, what do you think is a more effective way of inviting somebody to your party? Do you think it's better to well, you need them at the party, so let's just give him the entire house. Let's just move the house to him. Does that seem very effective? Well, no. If the house was small, right? Which, like, what I mean by that is if it was just like one slot, so it's just an integer or something, sure, that doesn't cost anything. But let's say it was like a group, like a whole array or something, so it's like a big house. Well, it's actually easy to just give him an invitation, a little piece of paper that says 3 on it. Now, he will take this piece of paper, instead of taking the entire house, he will read it, look at the memory, and say, oh, this is 3, so the house is here. Now, in this scenario, we're pretending like this invitation right here is actually what a pointer is. A pointer is just, well, it's also a data type, but this data type just stores a memory address. That's all a pointer is. It's a very simple concept that can be a little bit confusing depending on how you use it. Now, let's get into the code and show you different examples of how we use it. Now, we'll just make a new file. Oops. Just make a new file here. We need this. Let's just call it pointers.c. And we're going to use our stdio.h library, and we're actually going to be using another function other than print. We're going to be using scan in today's video. We're going to learn about how that works, and that's important because it's actually like one of the simplest ways to have input. We're going to be able to type something for the program. Now, we're just going to start off, create our main. Okay, now, let's say we have an integer x, and that integer is equal to 10. Okay. Now, how do I make a pointer that points to this variable 10? Well, first of all, we actually have to specify the data type of the actual variable. In this case, it's an integer. And then we use this asterisk operator followed by the name of our pointer. We're going to call it pointer x. And, well, we can actually set it to a number, but that doesn't do anything. We're just giving it our own memory address, and we're pointing it to some piece of data in the memory, but we don't know what that piece is. It's undefined behavior. It's going to be different every time you run it. So instead, we want to pass the address of the variable x, and we do that by using the ampersand operator. And when we stick the x to it, well, what this does is actually it returns the value of, well, the memory address of x. And, well, right now this just prints x. Well, let's say I wanted to actually use it, right? So let's go and print this pointer. And to print a pointer, we actually we use the %p, and let's just make a new line after, and we can pass pointer to x. Okay, well, we're printing the pointer, right? So we should get the value of x, right? Well, not quite, but let's see what it gives us. We get this. Now, I'm going to show you that. See, we get a different number every single time. This is a number. This is in hex. It's a different number system to binary. It's also important to understand this. I might be doing a video on it to cover it later on, but we'll see. Anyways, well, we just printed that piece of data, and what did we see? We saw a different value every single time. And that's because memory is being allocated differently every time we execute the program, right? There's nothing in C that says, oh, well, memory needs to be allocated in this certain order where these slots are always used for this. We can't really define that, and we don't need to. That's kind of useless. So anyways, but we didn't do what we wanted it to do. We printed the pointer. We didn't print the actual x. We should print the number 10, right? Okay, well, first let's switch this to a d because that's for a decimal integer, right? And now if we were to print this, let's see what happens. Compile. We get an error. This expects an argument of type integer, and this gets an integer asterisk, which just means pointer. Because even though this says integer, this is not an integer data type. It's just pointing to an integer. So what we could do is actually use the asterisk again. And what this does when it is not used to define a pointer is this is a dereferencing operator. And what this means is that it looks at pointer x, it sees the address, it goes to the memory, and it pulls that variable. It's just like the analogy. It looks at the invitation, it sees the address of the house, and it knows where the house is. Now, if we were to compile now, we shouldn't be getting any more errors. And we get 10. Perfect. Now, we just proved that we can actually access this data, but can we mutate it? So, can we actually just like change the value of x to -2, for example? And of course we can. We do the same thing. We use the asterisk operator, and now this is the same thing as just writing x. And we can set it to whatever we want. -2. -2. Perfect. So now that we know how this really works, well, let's see the first use case to this. Let's say we want to create our ×2 function. Now we're going to make this a type void, and remember this means that it returns nothing because um, double the value of whatever we pass without actually having to return any number. So we're going to ask for a pointer as our parameter. And here, we're going to take this pointer. We're going to multiply it. We're going to set it equal to whatever the pointer is times 2. We don't return anything at all. Okay. And here, if we were to print this %d, this is our old. And if we just print our x here, oops, let's just stay consistent, and we won't print x. We'll actually no. Yeah, okay, we'll keep it like this. We'll actually just print x, and this is our new. And in between them, we're going to call our times 2, and we are actually going to pass, well, the pointer to x. Now we can either do this, or we can actually just directly do this. And let's just comment this one out for now, and we'll prove that they both work. Oops, we forgot it here. I think that should be all. There we go, we double. Now let's prove that the other one is okay. And it works. Now you might be asking, if you forgot what we went over in the video where we talked about scopes, well, why is this important? Why can't we just pass a integer x and then take that x, multiply by 2, set it equal to x? We can do that too, right? Well, there is a little bit of a problem with that. And how scopes work is this creates its own scope in the stack. What that means is this x is not the same as this x, even though they're passed here. What happens is when you pass it here, it actually just copies that value and assigns it to this new x, right? When we pass a pointer, the same thing has happened, right? It's technically not the same pointer, okay? If you were to have a pointer to this pointer and a pointer to whatever pointer comes through here, they would be different. But since we copy the value of the pointer here, all we care about is that value, because that value carries the memory address. And then when we use the dereference operator, even though it's technically a copy of itself, I'm sorry if that's a bit confusing, it's still pointing to this x. So now when we pass the x itself, it won't work. There you go. It doesn't change at all. But if we were to actually print it here, just to prove that, well, it actually still is, let's call this middle. It still is doubling the x that we passed through. It's not like we changed anything about that. See, the middle is 20. And that's why this is very important. We can mutate variables outside of their own scopes. And in the coming videos, when we talk about arrays, you'll see why this is even more important, because C doesn't let us pass entire arrays as parameters. They might be too big, and it's very inefficient. Now, we can talk about scanf now. Let's say, well, first of all, let's switch this back to whatever it was before. We'll keep it like this. We don't need this. We already know it works. And let's just pass this. Okay. Let's say, you know what? From now on, I don't want to decide what x is before. I want the user to actually decide what x is. That's where this function scanf comes in. How does scanf work? Well, it's similar to print, which we have to use these operators. This is the decimal one, and this means that we're expecting the user to input a decimal, right? And here we give it the variable that we want to change. But we just talked about how if we send in a variable to a function, it can't actually mutate it because it's sending in a copy. So we had to send in the pointer to it. We could have also sent in this, but we said it's the same thing, right? So, see, it didn't execute. Well, it did execute. The program is running, but it didn't do anything. That's because it's waiting on me for some user input. And there you go. X is not 10. It's whatever I put X to be. Now, an interesting thing about it is, let's create a new integer called return. Well, let's call it RET because that's actually a name that we can't use. And let me show you what it actually returns. And this will be a decimal integer. We'll print return. And yeah. Prints 1. Now you might be thinking that that's because, well, that might be an exit status, which, like, you're not wrong to say that. But if we were to have a second int y, I'm actually not sure if this would work. I haven't tried this before, but I believe it should. If we were to ask for two different integers, 1 and 2, we return 2. So what this is actually returning is how many of these we actually successfully returned. Which it asked for two integers, and if it got two integers back, then it'll return 2. That's a good way for us to know if if we succeeded or not. And if I were to pass a character and the letter 3, we return 0. We didn't get any correct. And if I were to pass a 3 first and then the A, we return 1. Because it terminates as soon as it sees the A and it sees that it's the wrong type, it just terminates. Now, how can we use that to our advantage? Let's write a piece of code. We're gonna write some code that doesn't continue until it receives until it receives a integer. So we're just gonna have a for loop that goes on forever. We're gonna break it somewhere in between. We don't care about return for now. We're gonna keep taking in this, and actually let's set return equal to that, and let's say integer return if return equal to 1. We're gonna break, and that just means we end the for loop. Notice it never ends, even when we give it an integer. And there's a good reason for that, and it's because of a important property of scanf to know. It doesn't actually remove anything from the standard input. And what I mean by standard input, it's this stream right here, this stream of letters that I'm giving it. The second time that I ask for scanf, well, it's gonna actually read this 4 A's before it reads the 1, 2, 3. So automatically it actually fails. So what's the solution? Well, if it fails, what we should be doing is actually let's just store some character C. And we're going to say scanf is %C. Let's remove this new line. We don't need it. And what this will do is, well, if we didn't get the right type, well, we're just going to scan again, but we're going to save it as a character. So now if I do this, it actually works. What did we do here? Well, we said that scanf doesn't remove data from the standard input unless that data is the correct data type. If it looks at it here, it's asking for a decimal integer. If it sees a character, it'll just stop. It'll leave it there. Something went wrong. That character doesn't belong there, so it's not going to remove it. So what we will actually do is, well, if we didn't get the right number of correct data, well, we're just going to do scan again, and what it's going to do is it's going to read whatever we left there, and instead it's going to store it in C. But because it's the correct data type, we're actually just going to get rid of it. And this loop will keep going over and over again until we clear the standard input from any character that's not a decimal integer. And it'll keep going until we find one. So yeah, that's it for today. We talked about pointers, we introduced them. Now they can get pretty tricky, so I would recommend you get a good wrap around them. They are a very simple concept. A lot of people try to overcomplicate what they really are, but we can do a lot with them. We learned how to use them in functions, how they act as an alias and not just as a copy. So that means that we can actually mutate whatever data they're pointing at. And on top of that, we introduced the scanf function, and we talked about how it treats standard input. Now, thank you guys for watching, and I'll see you again in another video.